Okay, P-Chem students, welcome to the last video for our big idea review for your AP Chem exam, which is next week on Monday, at least in the 2022 year it will be. We're going to go through and talk a little bit about thermodynamics, very little, and the majority of it's going to be electrochemistry. So let's go ahead and get started. At the end, I may remind you of a few things. We'll see how that goes. Okay. So here we go. So big idea 9 actually blends a little bit of the thermochemistry, especially delta G and solving for equilibrium constants. And we kind of tied this together when we did electrochem. We actually did the free energy and cell potential in the same unit together, which was actually a good idea. So we'll start over here on the left again, as usual, and discuss the, there we go, and discuss these ideas individually. So to start with, entropy is actually, and you guys know entropy, a measurement of the quantity of the disorder in a system. If something has a positive value for entropy, it means that it is messy. It has a high entropic value. If something has a positive S or a change in positive S, what that means is that the products have a greater entropy value than do the reactants. This means that, you know, if you have water and it's producing hydrogen and oxygen, both of which are gases, of course, you have not only a molar relationship change from 2 moles of something to 3 moles of something, but you also have, in a lot of cases, a liquid going to 3 moles of gases. This would be an increase in the entropy of the system. Calculating it, if you're given the standard entropies of formation, would be pretty easy. You can just do the subtraction of your products minus your reactants. Same way you would calculate for enthalpy values or delta H values as well, as one of the ways to calculate that in our thermo unit. One different thing about entropy values, however, is that the units for them are in joules per Kelvin mole. Being in joules, you are going to have to convert them to kilojoules to be used in the same equations, for instance, in your Gibbs-Helmholtz equation. But individually, they can just be calculated in joules. You could, of course, change everything to joules, which would be fine. But you're going to have to do one or the other. The reason these values are in joules is because the values are so small. If the values were in kilojoules, you know, when you have 30 joules per Kelvin mole and saying it's 0.03, the number's so small, so they actually use joules for these instead of kilojoules. That's the only reason I can think of why. But it is, the entropy is a measurement of the quantity of disorder in a system. If something had a negative entropy value, it means it's actually effectively becoming more ordered as a result. Your free energy is a little different, of course, but it relates to the entropy of a system. The free energy of a system is the amount of energy that's available to do work. So it's called, you know, potential energy, which actually is measured in voltages or in voltage, to do work in a system. So if it is negative, it means that it is thermodynamically favorable. And we would prefer you use this term as opposed to spontaneous. I think both are acceptable. They're certainly not going to cause things or count you wrong for writing the word spontaneous, but it is better to say it is thermodynamically favorable than it is spontaneous or non-spontaneous. If something has more energy than necessary for a reaction to occur, it means that you're going to have energy left over in the system. If energy is left over, it means you had enough energy. So that would mean that that reaction is in fact spontaneous. And the delta G value, if you subtract products minus reactants, giving you a negative value, that would mean that there's energy remaining. And so there is enough energy to do work. That's what that really means. So when you do the subtraction, you find out that G is a negative value. It is thermodynamically favorable because there is excess energy to do work. That value isn't going to be in kilojoules per mole. If you have to use Gibbs-Helmholtz like we're showing you over here, you would need to change one of the units, preferably the entropy unit, but it doesn't matter. You could change both your enthalpy and your Gibbs free energy, and that would be okay. So when you're looking at the signs for sign convention, determining whether something is spontaneous, and we've done a lot of this through last year and again this year, is look at the signs of what you have in your, and you can play the math game with it all you want to, but I hope you guys can do it simply with the signs. If the signs of, and this is a column for delta H and a column for delta S, not a column for temperature. Temperature is going to be in Kelvin, so it's always positive. But your temperature, oh, excuse, that's not the eraser. For delta H and delta S, if this is a chart of those signs, the sign convention for each of those, if they are different, in other words, if one is positive, one is negative, they're always going to be one or the other. They're going to be spontaneous or non-spontaneous. Or if you want to say they're going to be thermodynamically favorable or not thermodynamically favorable. If it is positive and you're subtracting a negative value, you will always get a positive value. So when those signs are different, the delta G value can be determined. The favorability can be determined quickly. If, however, those signs are the same, like say this was positive and delta S was positive, it is going to be dependent on the temperature. Temperature is going to drive this reaction. So, or you could say that the entropy value is driving the reaction. It's fine. But it's going to be dictated certainly by the second term of the Gibbs-Helmholtz equation, which is this equation up here at the top. If in fact the signs are the same and both negative, then once again, it looks like it's going to be, well, it's already exothermic, but the entropy value is going down. So if you increase the temperature here, you would be subtracting a negative, which would mean that at really high temperatures, this could actually be positive or non-spontaneous. So it would depend. It becomes temperature dependent when the signs are the same. Just kind of something to think about. Okay, so going back down here to delta G's again. Delta G can be calculated using your Ratlink equation. This equation is given to you on your formula chart. If you know what K is, you can solve for delta G. If delta G is negative, what it really means is that that K value right there is a value that is greater than 1. You're going to have more products than you had reactants, right? And so a higher numerator, and that this negative sign kind of takes that into account. It'll end up giving you a negative value for delta G. If it's less than 1, then it's not favorable. You're going to have more reactants than products. You're actually going to end up getting a positive delta G value. And you can plug numbers in and solve using your Ratlink equation to see if that's the case. The same thing is true with your Neffy equation. Also, both of these equations, of course, are given to you on your formula chart. But if your cell potential is positive and it says negative in number of moles of electrons times your Faraday's constant times your cell potential, if that value for cell potential is positive, your delta G will be negative. So if you have negative delta G, oops, using my eraser again. If you have that negative value for delta G, that means that your voltage is actually going to be positive. Both of those will indicate a thermodynamically favorable or a spontaneous reaction. If you see us write something, or you see written delta G naught, or I didn't write a delta, or delta H naught, or delta S naught, what the naught really means is standard state. And you guys should know this, but what it means is that those solutions, if they're solutions or if they're gases, are at a constant temperature of 25 degrees Celsius. They are 1 atmosphere of pressure for gases and 1 molar solutions if they're in solution. That's how those values are determined. If the concentrations are manipulated, then there's going to be a change in what your cell potential is or what your delta G is. And that's where we use the Nernst equation to figure that out. Okay, so let's move up here a little bit and talk about some stuff that we've already talked about, but we'll hit it again. And I might even throw a little bit extra stuff in there as well. If you change the temperature, you increase the number of particles that are moving. They're moving faster. There's going to be more collisions. If that's the case, you're going to get things to dissolve, increase of dissolving. So your solubility is going to increase, mostly for solids mostly for solids, I should say. For gases, that has the opposite effect. You would increase the rate of decomposition or cause decomposition to occur. You also increase the volume of a gas and so forth. You also will increase phase changes going solid, liquid to gas. Be very careful though, because they may throw all this stuff together in one equation. So if I were to draw a heat curve here, yeah, and so let's say it's just water and I've got 0 and 100 for my solidification and vaporization. And let's say I'm going down here from say -12 to up here at about 80 degrees C or so. So what's happening if I am going from -12 degrees to 80 degrees? Is it endo or exothermic? A lot of my students, especially in advanced, will say, oh, it's exothermic, it's hotter. Not true. In order to go from here to here, you must absorb energy. That is an endothermic reaction. Some of you are laughing, going, Tell it, why are you even saying this? I'm saying it's like, I don't want you to miss something simple. If in fact you're going down in temperature, I realize it's getting colder, but it is actually losing energy. So for this one right here, delta H would actually be negative. For this one up here, delta H would actually be positive. And so you can think about those also in terms of spontaneity as well. Kind of, you're actually increasing entropy, so it's going to be, a negative minus a positive. So in fact, it would it would be negative going down, that is. Okay, so anyway, I just wanted to kind of discuss a few of those things with you. Over here, the activation energy does relate to delta G. Delta G does not tell you how fast something is going to occur. There's no equation, oh, I've got this much free energy, that means it goes fast. That's not true. What it tells you is whether or not it is thermodynamically favorable or spontaneous. It doesn't tell you how fast it's going to go. Now, this graph over here may tell you relatively how fast it's going to go. If you compared to, you could say my second drawn graph is going to go more slowly. It requires a greater amount of energy to occur. Not necessarily free energy, but requires more energy. So if it requires more energy to occur, or before the reaction gets started, then it's actually going to take longer for this reaction to occur. Doesn't mean that it's not going to happen. If you throw a piece of iron in the road and come back a week later and it's rusted, it didn't happen overnight. It took a while. It took exposure to the elements over time. It just didn't happen fast. You could make it happen faster, but that's a different story entirely. But just because it's spontaneous doesn't necessarily mean that it's going to be fast. And so that's kind of what we're saying here. An unfavorable or slow process could be coupled to a highly favorable process if you have enough activation energy. Now, if you were to heat the system up, you're really not changing the amount of energy necessary for it to happen. You're just giving more of the molecules the necessary activation energy. We talked about that using Maxwell-Boltzmann distributions, and you should be familiar with that already. You don't change the curve at all. The only way to change the curve is to add a catalyst, right? And then lower that amount of energy necessary because you've taken care of the alignment part. Giving it enough energy part is the temperature. Okay. So let's move down here. Let's go ahead and do the cell. So we'll go ahead and build the galvanic cell. So, and we'll build our galvanic cell down here on the bottom, but first let's talk about what they want us to do. So it says, build a galvanic cell, yay. Using silver and copper metals in their solutions and their solutions. Calculate the cell voltage. Let's go ahead and do that part first. So I'm looking at these two reactions right here. And I'm putting silver and copper together. It's going to be, I already said, a galvanic, which is the same thing as a voltaic cell, which means that my cell potential is going to be positive. So I've got to change one. I can't have reduction. I've got to change one of these so that I actually have an oxidation potential written here as well. So I'm going to reverse my copper reaction to produce copper ions and my 2 electrons. And that would change my cell potential here to be a positive 0.34, right? So those would be my 2 half reactions. Now up on the top, I am going to have to alter my silver reaction before I add them together by multiplying by 2. Remember, you do not multiply the cell potential by 2. You merely multiply the reaction. The fact that silver is going to give off a certain amount of voltage regardless. It's not based on the number of electrons that are transferred. It's based on silver itself. It is inherent to that. It is internal to silver and to copper as well. So if I go ahead and I write this out, this would be copper plus 2 moles of silver are producing, silver ions are producing 2 moles of silver and copper ions. Don't it? Get a little lost there, aren't you? Plus copper ions. There we go. Looks like calcium. That's Cu2 plus. And if I calculated that cell potential, adding that together, that ends up giving me 1.14 volts for my total. And I'll kind of show you that right there. So we calculated the cell potential here, cell voltage. We wrote a balanced net ionic equation for the reaction. And then we're going to label the cathode and anode. And we're going to write the line notation for this as well. So let's go down to our cell and kind of diagram this guy. So I'm going to write copper over here on the left, and I'm going to write silver over here on the right, because that's how they normally go. It doesn't necessarily have to do that. It could be drawn the other direction. It doesn't matter. I do know that going up to my reactions here, copper is going to lose electrons. So this is going to be the site of oxidation. So this is going to be my anode over here. Copper is going to lose electrons. So the electrons are going to be lost. They're going to travel in this direction over to the silver. So that means silver is gaining electrons. So this would actually be my cathode. You can remember this as electrons are going to go from the anode to the cathode, right? Or if you like, cat, yeah. The anode is the site of oxidation. You can remember that as anox, and the cathode is the site of reduction. Sorry, so you would have red cat over here to remember that. Sorry, I'm getting distracted. Red cat. So I would write my solution of my ions here. So these are Cu2 plus ions here. And this would be in a bath of the silver ions here. Let's go ahead. It didn't say anything about the salt bridge, but this right here is the salt bridge, right? Let's go ahead and call my salt bridge or fill my salt bridge, say with potassium nitrate. That would be a good description of what's going on here. My voltmeter is going to give me my 1.14 volts, of course, if these are both 1 molar solutions at 25 degrees C, or at least the concentrations are the same at 25 degrees C. We'll go ahead and leave that. And that's our salt bridge, fine. So if I were to write like my half reactions here, I've got elemental copper going to the cuprous ions and 2 electrons. And over here I have the silver ions adding an electron to produce silver. So what's happening here is the silver ions are precipitating on here as this becomes more negative from the electrons. This losing electrons, the copper is popping off into solution and producing copper ions. To accommodate for this and maintain cell neutrality, the salt bridge is actually going to dump ions in there. So in this case, I'm losing positive charges. So the potassium ions are going to dump in here to make this continue to keep it positive. The loss of positive ions, did I say this right? Yeah, no. The gain of positive ions, sorry, on the other side. Yeah, I'm saying this right. Nitrate ions will go in here to accommodate for those. And that will keep the cell neutral in both compartments. Now, when is the cell going to die? Okay, so I'm looking at 1.14 volts, but that voltage is going to continue to go down as the cell runs, right? Just like a battery will go down as you use it. What's going to happen is these silver ions are going to be depleted. Now you're dumping potassium ions in there, but that doesn't matter. Potassium is not going to produce elemental potassium on the silver. So once it's complete and I'm run out of ions, the battery is dead. Something else that could happen, which is probably more unlikely, is that the copper electrode could be depleted, giving all the copper ions in solution, no more copper present. I think it's much more likely that you'll run out of ions in the silver in the cathode, but whatever. You could also break the salt bridge or run out of ions in the salt bridge, or salt bridge dries up somehow. There would be no continuity there. Or one of my students today in class said, oh, you could just cut the wire. Okay. It's not going to cause it to go dead, but it will stop the cell from working anyway. That's interesting. So let's see. Deviations from these standard conditions will change kind of the equilibrium of the system, and it cause it to shift right or left. You can use Le Chatelier's principle to discuss this. As far as the equation to solve for this, E equals E naught minus it's RT in F or RT over in F, and then natural log of Q, where Q, I'll go ahead and write that on there. Q is actually going to be your product concentration divided by your reactant concentration. Okay, fine. This is the Nernst equation. You can use this to solve for this in the relationship of products to reactants. If they tell you something that is at equilibrium and you remember this equation, because this is not one of your given equations, I would assume that they would give it to you, but perhaps not. Anyway, E naught equals 0.0592 over N, and this would be log K if we wanted to solve for it that way. If you know you're at equilibrium, you can solve it this way, because what happens at equilibrium is that this value and this value are going to be the same. So this is actually going to be 0, and you can just, oops, and you can just set the equation up again just to be E naught equals to, and I've squeezed it all together, and you guys have done this in class. The RT in the R value, the temperature in kelvins at 25 degrees C, and Faraday's constant, and the integration of natural log and log, I'm putting all together as 0.0592. This will make it a little easy to solve for whatever your cell potential is at equilibrium, or to say it's at equilibrium and calculate your equilibrium constant. But you would need to know that you're at equilibrium in order to use this. If you don't know, then you've got to use the one on top to solve. Now, if they tell you that your product concentration and your other concentrations, in this case, for the, oh, what the heck happened to my pen? It's starting to mess up a little bit. Sorry, guys. There we go. If I have, in this case, I had copper going to copper ions, and I had silver ions going to elemental silver, right, with my coefficients of 2. My K value for this, or my Q value, my Q would be my concentration of my products divided by my concentration of my reactants, right? And this would, of course, be squared. So that could be subbed in for this down here, or if I knew I were at equilibrium, for this down here. If you increased the concentrations of the copper ions, it would cause it to shift back this way, giving you less voltage, which kind of makes sense, right? If I increase the concentration of the copper ions here, it's going to slow down the amount of copper that's actually popping off into solution. Same thing true here. If I add more silver ions, in here, it will actually go this way and produce a greater voltage. So you can manipulate what you're getting as your overall voltage with a concentration cell or with a change in concentration. And you can certainly use Le Chatelier's principle to describe that. You can also use, if you'd like, the Nernst equation and demonstrate the calculations as well. So if you look at this natural log of Q term, if you increase the product concentration, that number is going to increase, being greater than 1. Since it's subtracted, you'll end up changing that overall cell potential. So anyway, that's the math behind it. They don't give you the Nernst equation, so I would imagine that you could just, or you should, just use Le Chatelier's principle. But if you remember it, you're more than welcome to discuss it, explaining the experiment or explaining what's going on. That would be okay. So down here on the bottom, did I do everything? Oh, you know what I didn't do? Got it written down here for a different problem. But I didn't do my line notation. If I go up and I check for here, the things that I forgot to do, I said label the cathode and anode, I did that. But write line notation, I didn't do that. So let's do the line notation real quick for the cell we've drawn. So I had copper as my anode. That's what you always start with. Draw a line. Then you have your solution. Had they told us what that concentration was, I could have put in, 1 molar or 0.1 molar or whatever it was. And then I had silver ions, right? Silver ions. And let's say that I needed the concentration of those as well. You don't have to write them if they don't tell you what they are, but if they did, that's how you would write them. If you had an ion-ion system instead of something like this, you would use an inert electrode to do it. And then perhaps you would have, say, Fe2 plus and Fe3 plus. And then maybe you have the same silver cell and maybe a silver electrode. If you're doing something with ions or something with gases, you'll need an inert electrode as your actual anode or your actual cathode. Platinum doesn't have to be the first thing you write. It could be the last thing you write, depending. But it's always going to go from anode to cathode when you do that line notation. Okay, I forgot about that. I'm glad we went back and did that. So let's go to the last part here. It says the diagram shows an experiment to electroplate an object. Let's say the object is made of copper, or it doesn't really matter what it is, but we're going to plate it with silver. What we're doing is we're increasing the voltage so that the electrons are actually traveling in this direction, right? Which is contrary to what they would normally do. I'm plating a metal that has a higher reduction, or I should say a more negative reduction potential than does silver. So what's going to happen is if I pump these electrons this way, the silver ions are going to pop off in solution. I already have silver ions in the solution, and they're going to precipitate on here as they're reduced to make elemental silver, and you can plate that object. To do this requires that we pump energy or current in that direction. You would have to have a voltage that's greater than the voltage required for this to occur, but they want us to calculate the approximate mass of the silver deposit on the object. there's two ways these equations are asked generally. One is that they ask you how long it will take, in which case you solve for time having been given the mass, or you solve for the mass having been given the time. And in this case, we're actually given time. So we're given 30 minutes where this current is applied. I think this is enough room. I guess we'll see. 30 minutes where it is applied, and our current is 8 amps. So what an amp is a coulomb per 1 second, right? And so what I can do is change my minutes to seconds, change my seconds to the coulombs, or which are I'm using the amps that they're giving me. And then there are 96,485 coulombs, that is on your formula chart in case you forget, per 1 mole of electrons. Oh, look at me, 1 mole electrons. And for every mole of electrons, there's 1 mole of silver ions, because it's an Ag plus 1 mole of silver. I didn't have enough room to do the last step, but 1 mole of silver has a molar mass of 107.87 grams of silver. And so I could go calculate what mass is actually going to be plated on here, and it'd be 1.61 grams of silver. That would be my answer there. So that kind of takes us through, sorry, I was kind of all over the map there, but that takes us through our last big idea. This will be the last time that you actually hear us like stand in front of you and lecture talk stuff, which that's refreshing for you, I'm sure. We will actually be available, or at least in our district, I know we are. We are available to give you guys a hand if necessary. Let's stop doing that. Give you guys a hand if necessary. We'll be in our classrooms before and after school to help. I will see you guys Monday before the exam. I will walk you into the exam, and I will meet you after the exam. I'll have tissues if it's necessary. But I'm proud of what you guys have done this year, and I'm looking forward to see the results that we have. Okay, so that's it. That's the end of our review. I'll see you guys in the classroom.